My pool is turning, help, it's quite concerning, help, my phone is burning, help, please help me. When I got started cleaning pools back in the day, I never thought I needed any help in any way. But now I realize my habits aren't so good. I'm opening up my mind to learn the way I should. Help me if you can, my water's bad. And if you'll teach me what is wrong, I will be glad. My customer now doubts me and they're mad. So won't you please, please help me? My pH rises every week past 8.3. No matter what I do, I can't hold free chlorine. I'm in ideal ranges, 110 alkalinity. But I've got scale and little flakes, can't you see? Help me, I've got algae, my water's green. I've tried all the algicides and shock chlorines. Yet the next day chlorine's gone, how can it be? Won't you please, please help me? When I got started cleaning pools back in the day, things just seemed easier in my mind anyway. But now I recognize the problems that I face can be prevented, so I've got no time to waste. Help me if you can, I'm listening to the Rule Your Pool podcast while I clean. Though I could do without those stupid songs you sing. So won't you please, please help me?
Hey everybody, welcome back to the Rule Your Pool podcast. This is episode 143, and with me, as not as often as he should, Jared. Good to have you back, co-host.
I am happy to be back here, and I just want everybody to know that we're going to have some housekeeping items to address. There's nothing like starting an episode of Rule Your Pool with Eric giving a solid dad joke before he says, I'm recording. So, I'm happy. This is good. This is a way to start it off, Eric. I know you were trying to break the ice.
Well, we've had a tense day, Jared. We had a pretty rough go of it together as our friendship has dwindled in the past. Are you asking me to tell the dad joke again?
Absolutely. I'm a big fan.
Is a tortoise capable of telling a bad dad joke?
I'm at the edge of my seat, everybody.
Turtley.
Yes.
All right. Now, with that out of the way, let me get my Orenda hat on. Jared, I screwed up in the past couple weeks. Obviously, we got a lot done last week with filming at my pool, the renovation, and I want to thank Microglass again for that. I want to thank Pentair for coming out. It was a lot of content that we filmed. But in the process of that, we missed one of our weekly meetings, and I completely dropped the ball and whiffed on it. So go ahead. I know you've been wanting to vent about this. Let's get it out to the world because I have nothing to hide.
Eric did not and has not read our weekly meetings notes. And I find that offensive. We were on our call today, and I said, Eric, I'm following up on this. And he said, I haven't seen it. And I said, well, have you read our weekly notes? I didn't get it.
Yeah.
That was false. He did. He just didn't see it.
Well, I wasn't lying, but I just want you to know that I have no idea what it feels like to put effort into writing notes and then having somebody that I depend on not read those notes. I can't imagine what that feels like, man. I'm so sorry.
I'm just going to wing it. I'm glad you just did the same, but
well,
we're going to get over this.
Now that we have aired our dirty laundry together, let's actually add value to the customers, which is what we like to do on this show. This is episode 143, and if I didn't already put the audience to sleep in the last episode, it was pretty in-depth, and I know you haven't listened to it, Jared, so let me catch you up. We teach pool chemistry on this podcast, and what I'm trying to do this summer is really step up our game and get more into the technical specifics of how alkalinity works and a few other things. And in the last episode, 142, I introduced the concept of a pKa value. We talked about specific buffering systems and how alkalinity actually works. And in this episode, we're going to talk about something that we get a lot of questions about, and we've always just kind of shrugged it off. We're going to talk about cyanurate alkalinity. If you have cyanuric acid in your pool, you have an additional buffering system on top of bicarbonates in your water. And we're going to talk about that in this episode. Jared, anything you want to add before we get into it?
That one article you just referenced that I read the other day, the pKa values, that's a real snoozer. So I'm sorry for everybody if you're going to chug through that one, but let's get going.
All right, let's go.
Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go.
Let's go back, Jared, several years. We used to just have all the parameters for the LSI, and it used to just say alkalinity as one of them. It didn't say total alkalinity like it does now, and we didn't have the secondary readings to show carbonate alkalinity. What was the big question that we got which inspired the change to say total and show carbonate as a secondary reading?
Because people didn't know which one to input, because when you calculate the LSI, it specifically asks for the carbonate alkalinity as the number you use for the factors. Well, I'm a pool guy. Whenever I'm testing water, poolside, so forth, it's just total alkalinity. Mm-hmm. So that's what it input. Well, obviously, I know and you know, as going through the code and the inputs and so forth, we know all the math was done on the back end. But as a user, you didn't necessarily know that. So therefore, we got a lot of questions.
Mm-hmm. Yeah, it wasn't made clear. There are enough pool pros now that understand, hey, I have to do something to this alkalinity for the LSI. I have to correct it. And one of the common terms is corrected alkalinity, which does mean carbonate, by the way, when you're referring to the LSI. Carbonate being the system that goes from carbonic acid to bicarbonate ions to carbonate ions. That whole buffering system is called carbonate alkalinity. And we have a graphic in there. If you tap on the Orenda calculator, show secondary readings, and then tap the underlined carbonate alkalinity, you will see it in there. That's what we're referring to. But obviously, if we have to make a correction, if there's a difference between your carbonate alkalinity and the total alkalinity number above it, what is that difference? That's what we're going to talk about today. That difference is cyanurate alkalinity. And if you use borate, we do have that option in the app as well. That will also contribute to that difference. But let's just presume you're not using borate in this conversation, just to not complicate things. The difference between total alkalinity and carbonate alkalinity is this cyanurate alkalinity, assuming you have cyanuric acid in your pool, which almost every outdoor pool does. So what is that? And I want to give you a stab at it because this could be a pretty short episode. I can explain it pretty quickly. What is your understanding of cyanurate alkalinity, and how do we get to this carbonate alkalinity, Jared? Let's see how much you've been paying attention.
I don't know the answer to that, but what I am going to say is I know historically we've had that chart you referenced with the carbonic acid, the bicarbonate ions, and the carbonate ions, and that nice little chart, right?
Yeah.
Which was really cool because I didn't understand it for like the first 3 years until I had it explained to me, and then it made a lot of sense. But then I just recently saw a updated chart where I guess you or somebody smarter than you added the cyanuric alkalinity and the borate factor that fills into that chart. And I do have some questions about that, and I'm assuming that was the point of your question. How does this play into that chart? If you don't know what the chart is, I'm assuming we've updated the link on the app so that we can show the updated one.
Well, we're only showing it in carbonate alkalinity now, but that's a good idea. I can add it to the CYA to show the cyanurate alkalinity. That's no problem. I can put that in the app.
And basically, what impact or buffering impact does it have on the pH change? And is that the answer to the cyanuric acid
Cyanurate alkalinity?
I was going to say cyanuric acid alkalinity. But
as you can tell, listeners, Jared is an avid listener of our own podcast. So he might be struggling a little bit today. His brain is so fried from last week's episode.
I've listened to maybe 2 out of however many we've done.
And folks, he's not exaggerating when he says that. He really means it. He's actually not listened to many podcast episodes, which is hilarious because you call yourself a co-host. Anyway, let me kind of explain how this works. In the last episode, we talked about how a buffering system works. And a buffering system is basically an acid and a conjugate base pair. And the only difference between an acid and its conjugate base is the hydrogen concentration. So it either has a hydrogen connected or it doesn't. So a conjugate base, like bicarbonate, for example, can take a hydrogen ion and then it becomes carbonic acid. If carbonic acid loses its hydrogen ion, then it goes back into the conjugate base form. So the hydrogen's separated, and that's all based on pH. The lower the pH, the higher the concentration of hydrogen ions. Therefore, it's a higher concentration of this weak acid. And then as the pH goes up, the hydrogen leaves, and you get back to your conjugate base. There are a lot of these pairs. The question is how many of them are significant buffers in swimming pool water? Now, if you're listening to this, and I know we do have some folks that are not just in swimming pools, they're in drinking water and a few other applications. Thank you for being here, by the way. In swimming pool water, the dominant form of alkalinity is carbonate. It's going to be the bicarbonate ion, meaning that is the main conjugate base that you have in your pool that can take hydrogens. So if I add something like muriatic acid, I'm adding a high concentration of hydrogens, HCl, hydrochloric acid. The chloride breaks away, no problem.
And to clarify there, everybody knows that hydrochloric acid and muriatic acid that we use in swimming pools are the same thing.
Well, it's the same thing, but it's a different concentration. So pure
Correct.
hydrochloric acid, you should not be able to purchase anywhere, and I don't think you can. What we purchase is 31.45% or
Diluted.
less. Yeah, it's a dilution so that you can actually handle it. And it's still really intense. It's still fumes. It'll still burn your lungs. You got.
But I want people to understand that when we reference hydrochloric acid on really anything, we're talking about muriatic acid here. Because
Yes.
we're not using straight hydrochloric acid either.
Right. Yeah.
It's just we're trying to give you the formula name so you understand the components that they're dealing with.
Right. And in the new calculator that we're in development on now, spoiler alert, hope to have it out this summer, we are having two concentrations of acid now because you can get muriatic in 31.45% or you can get it in 15%. It depends on where you buy. So anyway, when I add muriatic acid to the pool, I'm introducing a lot of hydrogen ions. And the question is, where do they go? And the answer to that is they get bound up in the buffering system. They bind to bicarbonates. They neutralize alkalinity, which lowers your alkalinity in the water. And that's going to convert that alkalinity into carbonic acid because bicarbonate is the conjugate base. It converts to its acid, which is carbonic acid, and that lowers the pH. And what that does is it recarbonates your water, which goes back to our containing pH conversation with Henry's law. So I'm going to add acid. My hydrogen ions go to the bicarbonates, neutralize that alkalinity, convert it to carbonic acid, which increases the dissolved CO2 because carbonic acid is dissolved CO2, recarbonating my beer, so to speak, lowering the pH, and then that CO2 has to off gas, thanks to Henry's law, which brings the pH back up. And it's this whole equilibrium. It's like the ecosystem of how pH functions in water with alkalinity. But carbonate is not the only buffering system in a pool. And as you can already tell, there are a few others. We've already talked about borate in a previous episode, and borate, only if you use it, is actually going to buffer between its acid, which is the boric acid, and its conjugate base borate
Good question
ion.
there. You made a good point that we're adding hydrogen to the water. It's turning into carbonic acid, which is lowering your pH. And then we're off-gassing carbon dioxide,
Yes.
CO2. The hydrogen didn't go away. So
No, it didn't go away.
So where did it go?
It
went
rebinds to water, H2O.
H2O or the bicarbonate ions. It keeps moving up the chain. So you didn't lose the hydrogen. You just moved it.
Correct. So that's great. Believe it or not, Jared, that's a great point, and we are keeping this in the podcast. I can't believe I just said that, but you have a great point there. You know why we teach people? Well, you actually do know why, but why do we keep saying pH cannot be controlled? This is why.
Because it can be managed.
It can be managed. It can be contained, but it can't be controlled because hydrogens move. They move constantly. They're constantly jumping between compounds. And if pH is all about water, right? It's H2O. So if I'm Mickey Mouse, I got my two hydrogen ears and I've got my oxygen head. If my ear breaks off, that hydrogen proton is the acid, and then this OH negative, because I have an electron here. If you're watching on YouTube, that looked ridiculous, but it gets the point across. I'm, Mickey Mouse Van Gogh over here missing an ear. I'm the hydroxide. So the higher the concentration of a hydroxide, that's the base, and then the higher the concentration of hydrogen, that's the acid. If I introduce an acid, it's going to have a higher concentration of those hydrogens. They have to go somewhere. And then they can, intersperse, they can go back into water, they can rebind to alkalinity, and it's this whole equilibrium. And I don't want to get into all the mechanics and thermodynamics of it all, because quite frankly, I would lose myself.
Yeah, we've learned there's a lot of that. So
There's a lot
we'll
of
bypass.
it. Yeah, there's a lot of it. But I'm trying to keep this simplified. And I'm not doing a very good job of it, apparently. But yes, the hydrogens don't go away. They just move, or they get redissolved as part of water. Did that answer your question?
Yeah, because we're just saying these other things are gassing off and they're leaving and it's being left behind. So therefore our pH is going up because it's just moving to the other forms.
That's correct.
Or something
it's
else.
Moving. And the pH determines where those hydrogens are. Okay. It binding to things or not. So on the other end of the spectrum, because the buffering capacity of borate is above where we want it in swimming pools, it buffers against the rise in pH. So that pKa value, if I look at the chart, let me pull it up here.
And while he's doing that, just to clarify, everybody, he said the rise in pH. So the borate factor will buffer the increase in your pH, whereas the decrease of your pH is managed by the alkalinity. So alkalinity is balancing down.
By the carbon
borate's
alkalinity.
Balancing up. So these are two different things here.
Right. So the pKa value, as we talked about in the last episode, pKa value of borate is 9.2. The pKa of carbon and alkalinity is going to be 6.14, which is below where we want to be. Now, technically, both of these buffer against a rise and a fall. They buffer in both directions. It depends on which side of the pKa you're on. So if we were below 6.14, we would have increasing buffering capacity up to the pKa. But since our pools are typically going to be 7.2 to 8.2 realistically, it's between those two things. But as I said in the last episode, the pKa value is the negative logarithm of the acid dissociation constant. You get all that, Jared?
Ugh.
I know. Yeah, it's terrible. I can't think of a more complex mouthful, but essentially it determines where the acid and its conjugate base are in equilibrium, meaning they're 50-50. Like, where are they equal? The concentration of acid to its conjugate base, they're the same. And so we draw a vertical dashed line on our chart to show, hey, at this exact point, these are in equilibrium. I'll give you another example that's not a buffer, but it is an acid and a conjugate base. How about hypochlorous acid and hypochlorite ion? The strong killing form of chlorine versus the weak, I'm not going to say useless form of chlorine, but a much slower form, hypochlorite ion. Well, in this case, hypochlorite ion does not have the H in it, so it's HOCl for hypochlorous acid, and then it's OCl minus for hypochlorite ion. That means that hypochlorite is the conjugate base to hypochlorous acid. And in the industry, we're taught it's at 7.5 without stabilizer in the pool. At 7.5, they're at equilibrium. What it's really saying is that's the pKa value. Technically, the pKa value is 7.54, which I've had to revise this chart, by the way, Jared, because the sources we had years ago said it was 7.48. And now I'm seeing a lot of sources, shame on me for not checking more, but
Generalist,
I'm correcting it now.
can't believe it.
I know. I mean, 7.5 is close enough, but 7.54 is the pKa for these two things. And so we're adjusting our charts accordingly. All that is to say, when you have a buffer that can take or give away a hydrogen and neutralize acids like bicarbonate can do, the closer you are to that pKa value, the more intense the buffering capability, because you have more in both directions because the concentration is closer to 50-50. If I'm closer to the pKa, then that means I'm buffering more. Well, the pKa value of cyanurate alkalinity is going to be 6.9, which is higher than 6.14, and this is why it matters to pools. We don't have as much cyanurate alkalinity in pools as we do bicarbonate, usually, but we do have a higher pKa value, which means where we maintain the pH in our swimming pools is closer to that pKa value, which means the buffering from cyanuric acid and cyanurate ion is more intense than bicarbonate alkalinity.
There's just not as much of it.
There's just not as much of it. Yeah, that's exactly right. So if you're looking at the graphic that we have just recently created to overlay with cyanurate alkalinity, you will see that that pKa is closer to where we are. Now, we have a lot less of it, and I don't want to dwell on it. We'll just say this. The Orenda calculator has factored this in since the beginning.
Would that be the third?
Well, the third depends on the pH, but it's approximately the third. Yes.
But when everybody does the LSI factor, if you're not using our app for some reason, and they say factor in the third of your alkalinity as a discounting factor, is that third your cyanuric alkalinity?
That's exactly right. And I'm going to get to that in a second, but I need to close this thought before we talk about that. Do you have another question?
Well, I was going to say, you said it's just less. Well, you can see how much less. It's that third.
Correct. You have less parts per million of it. when we have cyanuric acid in the water, it's not just affecting chlorination. It's not just affecting the LSI. The way it's affecting the LSI is because of this cyanurate alkalinity. And we have cyanuric acid, and its conjugate base is a cyanurate ion. Like I said, the pKa is about 6.9 pH. When you have this in the water, if you add acid, a lot of it's going to get bound up to the cyanurate ion because that's the conjugate base, and it's going to get bound to that first because it's closer. There's more intensity of it because there's a higher concentration of that than there is bicarbonate ion, for instance, which is crazy to think about because we don't have high CYA in an Orenda pool. Ideally, we're 30 to 50 for a residential pool and 15 or less in a commercial pool per the CDC guidelines. So we don't have a lot. And if we take roughly a third of it on a commercial pool, that's about 5 parts per million compared to, the traditional 80 to 120, which most operators do. Not that I'm recommending that necessarily, but let's say it's 80. I think 80 is a pretty reasonable number, maybe 70 to 80. The standards allow for down to 60. If I got a liquid chlorine pool, I'm going to want my alkalinity in the 60s or 70s.
Well, let's just say it's all over the place depending on where you're located and how often you use trichlor tabs.
Right. So as long as I've got a reasonable amount of CYA and it's not hundreds, I've got a lot more bicarbonates in my water than I do cyanurates in my water.
I say at minimum, at least double.
At least double, that's for sure. Now, to your point, about a third of your CYA is going to be cyanurate alkalinity. It's not exactly a third, but the rule of thumb is close enough. Now, it depends on the pH. And that pH is going to determine whether it's 0.30 times your CYA, 0.31 times your CYA, 0.32, and of course a third is 0.333 repeating. Into the Orenda calculator, all of this is factored for you. So it takes your pH into account. It takes in these other factors. The exact math has been in the calculator ever since we did our major update for version 3.0. You will notice when you use the Orenda calculator, if you change your CYA level, your acid doses are going to change slightly. Not a lot unless you have a lot of CYA. So if I've got 90 CYA, I have approximately 30 cyanurate alkalinity, which is going to increase my acid dose slightly because I have more buffering capacity because the pKa is closer to where I am. If we took CYA out, the total alkalinity is all carbonate. Assuming I don't have borate and I don't have CYA, it's going to be carbonate alkalinity. So that is a direct relationship between my acid dose and my alkalinity.
You're telling me that if I have a higher cyanuric acid, let's say I am one of those people that has 150 or 200 parts cyanuric acid, I'm going to need more acid to lower my pH.
That's correct. So I'm going to do it right now. I'm just going to put it into the calculator and I'm going to put 80 total alkalinity. You can follow along at home if you're not driving. I'm going to go 300 calcium, and I'm going to say 7.6 pH at 77 degrees Fahrenheit. So this is a pretty standard starting point that we like to do when we teach. Actually, I'm going to start at 8.0, and I'm going to correct down to 7.6. So on the left side, I'm going to have 8.0, and on the right side, I have a 7.6. In 20,000 gallons, my correction at 80 alkalinity, 300 calcium, no cyanuric acid from 8.0 to 7.6 is going to be 14.61. I'm going to write it down. 14.61 fluid ounces of muriatic. Okay, 14.61 ounces of muriatic acid. My future alkalinity is going to be 77.15. Writing that down too. So I'm going to go down from 80 down to 77.15, which is our burn rate. And this is an important thing to know. If you're trying to forecast your chemistry, you want to know how much alkalinity am I taking out of my pool at a time. And a lot of people don't think about that. They think, oh, I run 80 alkalinity. Well, every time you add acid, you chip away at that number. So keep that in mind. Now, if I increase my CYA up to 20 and everything else is the same, my dose went from 14.61 ounces up to 16.84 of muriatic for the same correction.
That's a big difference.
That is a big difference. It adds up real quick. And this is just a 20,000 gallon pool. Now I'm going to go up to where people like to have it. Let's just say 50. We're okay with 50. We say don't exceed 50 in Pillar 4. We want to stay 50 or less on a residential pool. Ideally, somewhere between 30 and 50 is fine for cyanuric acid. At 50, my dose is now 20.18. So I've gone up with 0 CYA, it was 14.61. Now I'm at 20.18. That's more than 20%, right? That's actually more than 25% increase. And that adds up in your business.
That's costing money on top of having an impact on your chlorine's efficiency and other things.
Yep.
There's high cyanuric acid clearly is costing money.
Absolutely. And this is one of the other reasons why we say limit your CYA. Of course, we want you to hold chlorine for a week. Absolutely. We do. But you don't need to overstabilize. You're going to get almost all the protection you're going to get at 50. The reason that high CYA allows you to hold chlorine for a week is not because you're getting that much more sunlight protection. It's because it's slowing down your chlorine's kill times and oxidation speed enough that it just kind of drags out so that you still have it. Sunlight protection is not really dependent on water temperature at all. CYA's bond, once it's bound, it doesn't matter if it's cold water, hot water, sunny day, cloudy day, rainy day. By the way, Jared, it doesn't have to be a sunny, clear day for sunlight to destroy non-stabilized chlorine. Okay, it can be a cloudy, rainy day, just like I've been sunburned on cloudy, rainy days before. Those same UVB rays that go through the clouds, admit it, they're a little bit less. They are reduced a little bit, but they're still enough to destroy chlorine. So it's not just on a bright, sunny day that non-stabilized chlorine gets zapped out by the sun. It's every day. It's every day that the sun comes up. Okay, so just
not the sunlight, it's the UV rays.
It's the UV rays that you cannot see that go through and they break it down into hydrochloric acid and water, and we have a graphic in the blog. So CYA is very important for protecting against losing chlorine, but we're really talking about using chlorine that affects if you can hold chlorine for 7 days. So we went through all this like in-depth science in this episode, and I want to just take a step back with you, Jared. Let's make this practical for a pool pro. You are a pool pro, okay?
I thought I did that already. You were just talking gibberish, and I thought I clarified these items, but go ahead.
Well, let's summarize for people then. If smartass, okay, go for it, Jared. What have we covered in this episode?
Oh, you got to ask me questions. I'm just here to answer questions.
I just asked you a question. What did we cover in this episode?
Uh,
I guess you're not paying attention, are you? Gotta go. Come on.
Sorry, I wasn't listening. Go ahead.
I know. My feelings, if I had any towards you, they would be hurt.
I learned that hydrogen does not disappear, even though the CO2 is gassing off. I learned that cyanuric. Oh man, tongue
You're
twister.
good.
Cyanurate alkalinity
Yeah.
has a direct impact on how much acid we need to use for lowering the pH. Those are my only two takeaways.
Yeah. So cyanuric acid's conjugate base is called cyanurate ion. And roughly, depending on the pH, roughly a third of whatever your CYA level is going to be cyanurate alkalinity. The exact amount is calculated in the calculator. We're really precise on that. But that amount is going to impact your acid doses because it contributes to your total alkalinity. So not only is it telling you the difference between your total alkalinity and your carbonate alkalinity, which we display as a secondary reading, it's also dictating things like your pH ceiling. Because it's reducing your carbonate alkalinity, it's also going to reduce your pH ceiling, which could be seen as a benefit. But is that benefit outweighing the effect of higher levels of CYA on chlorination and your acid consumption and your costs? Probably not.
I'd say no.
Yeah. So anyways, I want to wrap this up and thank you for being here. I know a lot of customers have reached out through our help center, ask.arendatech.com, and have emailed us podcast@arendatech.com. Great ideas for the show. Thank you for that. We'll continue to do it because I think there's a lot more topics and I do have some cool guests lined up. I know I've said that 20 times now. It's just really hard to get them.
Not
because
me.
It's a busy time of year. Yeah, not you. I don't need to have you at all on the show ever, maybe ever again.
It has been a while, though. I will say it has been a while. Things have been going on. We're busy. I know everybody's surprised by that, but we are still busy.
Yeah, sorry for having to put up with our banter. I hope that you got some value out of understanding what that cyanurate alkalinity does and how it impacts the LSI. It does reduce that carbonate alkalinity, which brings your LSI down. And if you have any questions, look at our help center, ask.arendatech.com. See if you can learn more there. Read the blog. I put a lot of time into it, and I hope it helps. Thanks, everybody. And this has been episode 143 of the Rule Your Pool podcast. Take care.
Thank you.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.